As we prepare for final examination, we have a question from Science Paper 1 under the topic of Hooke's Law. So let's make this topic simple. So I'm going to read through this question, and this question is coming from section C of Science Paper 1. Now, a spring with its upper end fixed hangs vertically alongside a meter rule. The lower end of the spring gave the following readings in a table. Right, so we have readings like the first one, mass in kg, the second one, reading in centimeters, third one, applied force in newtons, then the fourth one, we have extension in centimeters. So what we are looking at here is what happens if a force is applied to a spring. So as you try to stretch a spring, you need to apply a force, and we are going to have an extended length, which we call an extension. Now let's have a look at the first question. So the first question is we need to state this Hooke's law. So the simple definition that we can give under Hooke's law, it's a law that tells us the relationship between the applied force and also the extension. So the relationship is that the two are directly proportional, which simply means that when the applied force is increased, so is the extension. So, right, so let's now define this. So we are going to say this law states that the force applied is directly proportional to the extension of the material. So this is one of the simplest definition that you can look at. Now we have question B. So under question B is where we are told to copy and complete the table for the values of applied force and extension in centimeters produced. So the first one, let's look at the first row. So we can see that this row represents mass in kg. Then the second one, we have the actual reading, which is given in centimeters. Then the third one will be the applied force. This is the force that is making the spring to extend. It is in newtons. Then the fourth one will be the extension. The extension tells us the distance that is expected when a spring is extended. Right, so now to make a sense of how we are going to fill this table, I want to give you some simple illustrations. So we are going to start with the applied force. So how do we fill in these empty spaces? So what you are supposed to do is, we know that weight is a force, and weight is equal to mass multiplied by gravity. Then we know that the gravity, if we round it off, we are going to use the 10 newtons per kg. So when mass was 0, the applied force was 0. Now what happens when mass was 0.02 kg? So let's calculate now the applied force. So I'm going to say weight is equal to, the mass is 0.02 times 10, which is weight is equal to 0.2 newtons as our final answer. So here we have 0.2. So this simply means that as long as the mass given is in kg, these numbers should be multiplied by 10 in order to find the value here. Right, so let's look at now the second one. So the second one is 0.04 times 0.04 times 10. So this will give us 0.4. 0.06 multiplied by 10, this will give us 0.6. Then 0.08 multiplied by 10 will give us 0.8. Then this should be, sure it should be an error, this should be 0.1. So 0.1 multiplied by 10 will give us 1.0. So that's what we are supposed to do when trying to fill up the spaces for the applied force. Now we can move on to the extension. Right, so now to understand that, I'm going to give you the simple illustration. So before any weight was added, this was the normal length of the spring, and from the table the normal length was just 10.0 centimeters. So this was the normal. Now what happened when a certain force was hung on this spring? So let's now look at the second illustration. So this spring extended a bit, so it gave us now the new value. So the new value is 12.0 centimeters. Then at this point a force of 0.2 newtons was added. Then we have our new length, which is 12.0. Now how can we find the extension? So to find the extension, we are just going to look at the total reading of our spring, which is 12 centimeters. Then minus the original, which is 10.0 centimeters, which is the difference is giving us 2 centimeters. So this is the number that we are going to put here. So that's what you are supposed to do. We move on to the second space. So under this one will be, we have, this is our spring, our spring. Then we add 0.04 mass. Then this time the extension, the total length of the spring now becomes 14. So to find the extension is this 14 minus 10. So the key point is you have to subtract the total or the original length of the spring before its extension. So we have a 4 here. Then here we have 16 minus 10. So 16 minus 10, we have a 6 here. 17 minus 10, we have a 7 here. 17.5 minus 10, we have 7.5 here. So this is what really happened. So that's what we are looking at. Now if you look at a point, when you are adding objects to a spring, it is going to reach a point where its extension will start to reduce until it stops to reduce. And from the numbers, if you look at this our first number from 0 to 2, the extension was 2. Then 2 to 4, the extension was 2. 4 to 6, the extension was 2. Then 6 to 7, the extension was 1. 7 to 7.5, the extension was 0.5. So if we kept on adding, it will reach at a point where the extension stops. So that is what we call the elastic limit. So that's a point. Now here, 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 here. So this is where we have now a direct proportion because the numbers had the same order. Now let's move on to question C. Right, so we have question C. where we are told to draw a graph of applied force against the extension. So here it simply means that the extension will be in the x-axis while the applied force will be in the y-axis. So this is where now you need to ask for a graph if you are not given one. So this is my y-axis, then I have my x-axis here. Now remember, under science you are not going to be given the scale. We are not going to be told that using a scale of this to represent that. So we are going to find our own scale. So remember, in the y-axis we are told is applied force, so I'm going to say force in newtons. Then in the x-axis, this is where we have now the extension. So now to come up with my own scale, I need to look at the numbers. So I'm going to start with the extension. So the extension, we can see that we have 0, 2, 4, 6, 7, 7.5. So the highest number is 7.5. So as long as, if you can come up with any scale, and as long as you are able to reach the 7.5, the last number, then that will make sense. So what I'm going to do here, I'm going to use this scale. So I'm going to say 2 centimeters to represent 2 units. So on your graph paper, that box, that square for 2 centimeters should represent 2 centimeters. So 2 units. So here we have 2 units, 4 units, 6 units. This is our 8 units. If I want, I can reach up to 10. The key point is that I've reached the highest number. Then from there, we are going to go into the y-axis. So the y-axis is applied force. Now for applied force, this will be 2 centimeters to represent 0.2 units, because we can see that from 0 to 0.2, 0.2 was added, 0.2 to 0.4, 0.2 was added, 0.4 to 0.6, 0.2 was added, 0.6 to 0.8, 0.2 was added, 0.8 to 1 is still 0.2. So the number is the same. That's the one that we are going to use. So we are going to have 0.2, then here we are going to have 0.4, then we'll have 0.6, 0.8, then here 1.0. So I'm going to start with the first one. So the first one is 0, 0, which is the origin. Let me just use a different color. So this is my origin. Then the second one is 2, 0.2. So in the x-axis is 2, in the y-axis is 0.2. Then we have 4, 0.4 somewhere here. Then we have 6, 0.6 somewhere here. Then we are going to have 7, 0.8, 7, 0.8. So the line will a bit bend. Then 7.5, 1.0. So now to come up with our graph, we can now connect. So the first point where we have the same numbers, we are expecting to have at least a straight line. So the reason why this line is not straight, because I'm not using the actual graph paper. So I'm not using the actual graph paper. Then here we are expected to have now a bending, at least a slight bending. The line not straight. So this is the concept behind the Hooke's law. So as we can see, the question is very simple. Now what is really meant by this directly proportional relationship? It means that when the force was 0, extension was 0. When the force was 0.2, if you use the graph, then the extension was 2. When the force was increased from 0.2 to 0.4, the extension also increased. When the force increased to 0.6, the extension also increased to 6. So as long as the extension is increasing in line with the applied force, that is the relationship we are referring to as a direct proportion. Then we have question D. On the graph, show the elastic limit. So the elastic limit is the point where the spring has stopped extending, or maybe the extension has started to decrease. So this is the point where we can say elastic limit. At times you may encounter a question where you are asked to, did the graph or the curve or did the spring reach the elastic limit? So if the line was to be straight, then the answer would have been no, if a question like that was to be asked. Now let's say if you are asked to find the extension, let's say the constant, so the formula is this. So the applied force is equal to K, which is our constant. Then we have X. Remember, X represents extension. So as you are trying to extend a spring, the force that you are using to extend is what we are referring to as the extension, the applied force. Then there is another force that will now pull against your direction. So this is what we call the restoring force. Now to find the K, we can divide by X here and also X here. So we have K is equal to applied force divided by X. For example, the applied force is 0.2. So we're going to say K is equal to 0.2 divided by what is the extension. So the extension is 2. Now remember, the extension according to our question is given in centimeters, but when finding constant, make sure you change to meters. So 2 divided by 100 will give us 0.02. So if you punch 0.2 divided by 0.02, you get the answer 10. So let's try another one. So let's say we use 0.4 divided by 0.04, we still get 10. That's why it is called constant, because at this point here, the K will be the same. Now if you are to find the constant at this point, the constant will reduce. So as the K is reducing, then the extension is also reducing. Therefore, the stiffness of a spring depends on the constant K. So if you find this video interesting, give it a thumbs up. Thanks for watching, subscribe and share.